Thank you, Torsten. I just need to find the clicker. Got it. Yeah, so one of the things I do in my presentations is I use my own photos. It just saves a whole load of difficulty about who's got the rights and stuff. So the ones with people in are official Microsoft photos. Everything else is my own holiday snaps, if you like. So I'm going to talk a little bit about grand challenge supercomputing, or supercomputing for grand challenges, if you like. And this is kind of the concept. I try and make the pictures relevant, so, it's greenfield thinking and all that. What if we decided that a challenge was important enough to make us change the rules of what we previously thought was possible or impossible? And that's, of course, what we're here talking about today. So what if we invested funding, people, time, and evolved the state of the art of what was possible with supercomputing? It's not a new idea. There's precedent for this. There's multiple precedents for this. There's some on the slide there. So there's the DOE program, or the ASCII program in the DOE in the US. When they stopped doing physical testing, which is probably a good thing that they did, they then decided to build a simulation program to be able to understand and quantify what was going on with the weapons. And so they decided they had to build an entire simulation program about this. That meant developing computing technology. It meant developing software. It meant developing people. It meant stretching over decades what was done. It meant educating funding agencies and so on. And that really is one of the biggest drivers of our supercomputing industry today. Another example is the Square Kilometre Array project. This is even more interesting because it started out as a multi-science group international collaboration discussion like we have now. So about 20 years ago, I was involved in some of the very early discussions of the Square Kilometre Array project, radio astronomy project, that were very, very similar to this. A bunch of scientists in a room saying, let's build the CERN for radio astronomy, or one of the many CERNs for radio astronomy. And it's interesting to see how that evolves. So one of the things they did was they set out a vision for how they wanted to be able to process large amounts of data off the radio astronomy telescopes. That meant they had to envisage computing capabilities that at the time were significantly bigger and more capable than what were available. And so they aimed high. And then in the meantime, the amount of time it took to build the international treaty that is now the Square Kilometre Array project, in other words, to get the project from a scientific vision to a real thing that's operating and running and doing science, it probably took best part of a decade longer than they originally planned. And that meant that those original computing visionary ideas, by the time they're up and running, they won't be ordinary because they're still large-scale supercomputing, but they would not be stretching the boundaries in supercomputing terms of what's possible anymore. Or at least otherwise they can re-envisage yet further again where they're going. So that's kind of one lesson, two lessons from this. One is these things take a long time to get off the ground to become reality rather than scientists in a room talking about a vision. And secondly is aim higher than you think on the computing requirements. Another example, which has happened at a much, much, much faster pace, is the whole AI revolution. A year ago even, never mind 2 years or longer, a year ago, we would not be stood here talking about how running AI models on supercomputers, large-scale computers, has changed the world. And yet it has. It's changed the world of day-to-day lives, it's changed the mass public, it's changed what we do in our professional lives, and it absolutely has changed the supercomputing industry. And then another example is the UK Met Office, which I'll talk about in a slide, where we're doing a collaboration where they sat down and thought, what if we did things differently? And there's a whole load of other things. This example over time of coming together saying, what if we changed the rules and we tried to do something that we previously thought was impossible? There's a list of them on the slide there, and there's many more. So back to that ChatGPT example. One of the things that, yeah, maybe we should do that. I don't know, has anybody in the room actually tried to put any of this into ChatGPT and find out what it says? It's built, it runs on supercomputing infrastructure. I mean, Nick's just been talking about that. Training AI models at large scale is a supercomputing challenge. In fact, having been involved in a number of different supercomputing application areas over time, I would argue it is one of the most challenging supercomputer applications out there. Particularly when you start to get to really large scale. It stretches things. And we're talking about running on supercomputers of similar scale to Frontier that Nick was talking about, or to Fugaku that Satoshi was talking about. Similar scale supercomputing infrastructures where you're running these big training models. But it's changed the industry. It's changed what we thought was possible about building some of these supercomputers in a very tight time frame. And when I say that Microsoft is building supercomputers of this scale, the plural is intentional. We have not built a Fugaku, we have not built a Frontier, we have built multiple supercomputers of this scale to run these problems and other problems. And that's changing the industry. It's changing where supercomputing people, HPC people, want to come and work. It's changing the employability in the industry. It's changing things like the supply of GPUs and the pricing of the supply of GPUs. So you can change the industry significantly. If we do what this room is talking about doing, you will have similar effects. You'll become an employment destination for people. You will change the market dynamics and so on. This slide says the same thing I've just been talking about, but it's not only doing that for the biggest applications, but it's being able to then roll that out for other people to make use of, makes you able to build workflows and services and infrastructure around it. And that's important. Building a supercomputer for a point project is fun, it's tough, it's challenging, but is very, very doable compared to a lot of the other challenges. Making it accessible and easy to use by a range of different entities, from the scientists who are writing and running simulation models, to people who are just going to be querying it for how it affects me as an individual or me as a company or potentially political stories and so on. That's a different level again. What are the workflows? What are the interactions? How do we interact with all of this data? One of the other examples I said I'd talk about where we can stand up and change the world or consider changing the world is the work that the Met Office is doing. So UK Met Office is a national agency in the UK for weather modeling and for climate simulations. They decided to step back and say, instead of running our normal procurement cycles, what if we took a 10-year vision of our computing needs around climate and weather simulations? That's not just a scientific statement, that's not just a technology statement, it's not just a procurement statement, it's a convincing politicians to fund a 10-year program, which in itself is a significant statement and a lot of effort. And then it's mapping out how you're going to interact with somebody over that time frame. And so they did that, and they ended up with a partnership with Microsoft as part of at the end of their procurement process to deliver this 10-year plan. And roughly speaking, this vision of changing the art of what was possible is split into two phases, Generation 1 and Generation 2. So in the Generation 1 time frame, it was really about how do we deliver a step change or a step increase in the capability we have. So same kind of scientific principles, one of the applications we're running now, but let's deliver a step change in capability, computing capability for those models. And there's some other stuff in there as well, but it's largely around that step change. But at the same time, while that's delivering science and new levels of science to the community, let's also do a Generation 2 thinking, which is what happens if we reimagine what's possible. Let's start at the beginning. What are we trying to achieve? What's the science questions we're trying to answer? What's the understanding we're trying to develop? But equally, as well as doing the new science, what are the applications of that science? It's the weather forecast, yes. It's the storm protection, yes. It's the understanding of the climate. But what does that mean? How do we deliver that as a value to society? Whether that means individuals, whether that means companies, whether that means governments. How do we take a leading role on the international stage and doing new capabilities around the science and the applications of science? And that was an important part of our thinking. And together, we will re-envisage what is possible on the technology front to achieve that as well. One of the things that is part of the Generation 2 thinking around the Met Office, one of the things that is part of the way that we approach the work we're doing with the ChatGPT training, and one of the things that you cannot fall over in the supercomputing field these days without being asked to talk about, justify whether you're doing it or not, of course, is cloud computing. That's a question this program is going to have to understand what role you have with cloud computing. I'm not going to sing it, but if you think of the Queen song, Who Wants to Live Forever, and at the end of it there's that piece of, what is forever anyway? That's kind of rings through my head whenever anybody says cloud. It's like, well, what is cloud anyways? Is it a technology? Is it a business model? Is it just buying stuff from Amazon or Microsoft or Google? It's not necessarily clear, and I suspect if we asked everybody in the room to vote, you'd end up with at least 7 different theories or definitions of what cloud is. That's exactly my point. That yeah, exactly. The observation, there's those fuzzy things in the sky. The important point is, and I'm sure you, more than most of my audiences, will recognize this, there are multiple different types of cloud in that image, and that's deliberate. There is no such thing as the cloud. There are a number of different companies who provide computing as a service and infrastructure and support and services around that, who choose to brand what they're doing as cloud computing, or whose customers have chosen to call it cloud computing. But each of us offer different things and different capabilities. Some of it looks the same, and if you stand far enough away, then a cloud is a cloud. But once you start to think about it, they're different, and they're in different ways, and they're having different effects on the environment around them, and different effects on the aesthetics and all the rest of it. And the same is true of cloud. There are significantly different things out there. There's different companies providing different things. It is global scale. Each of us has computing capabilities all over the world. We have a huge amount of network interaction connecting all this stuff around the world. We have people around the world. And so that's also something to think about when you're building this program, or envisioning how you're going to build this program. How does the global scale nature of work really, in practice? How many science projects really start by figuring out the international scale of what they're doing, as opposed to we're doing a research project here, and how do we collaborate with other people doing a research project here, very similar, and other people doing collaboration here, and so on. Actually thinking about it as a global interconnected infrastructure is a different problem. And so collaboration with the companies who are doing that might not be a bad idea to understand how to build these infrastructures. When you talk about a global, a climate version of CERN, for example, CERN's in one place. In fact, CERN has a huge center of gravity. Now, there's distributed processing around the globe, and there's scientists around the globe working on it, and the problems and so on. But fundamentally, the infrastructure is a high degree of center of gravity for that. You need to decide whether that's the right model or not. And arguably, particularly if you're going to try and, as Amora was saying this morning, involve the whole planet in this problem, then really you need to figure out how the infrastructure happens on a global scale. And the other thing to do is to transformational. Try and think about how the workflows you've always used could be reimagined. What about how it enables people to access the capabilities in a different way? And that doesn't just mean handheld versus logging into a computer or whatever. It means there's different skills and different people presenting different interfaces of the same capability, the same data set to different people depending on their skills, whether that's a politician or a climate scientist. Which kind of brings me on to this point. One of the other things that we do whenever we get together to talk about supercomputing in the science arena is we focus on the computing and the hardware. We always have done in our industry. Even if we take the scientists out of the room and we just get into the HPC people in the room, we'll narrow it down and we'll talk about the processes for 90% of the time, and then say, oh, by the way, it needs some interconnect and some storage as well. And then kind of expand that out to the science community. We talk about, oh, we need all the compute. And at the bottom of page 7, we'll say, please can we have some data and services and interaction and user workflows as well. We kind of need to flip that on its head. There are enough people, as we've already had 3 talks today, who are capable of helping and understanding and probably even delivering the technology side of what we're doing. The interaction with that as a science capability is probably something that is not possible. And that's one of the things. So one of the other things Microsoft is doing is this thing called a planetary computer, which is often assumed of as being a big supercomputer that's going to simulate the planet. It isn't really. Actually, the computing component of this is it's large, but it's not large by supercomputing standards. And it's really about taking a whole range of data sets from climate data sets, GSF data sets, Earth data sets, and so on, a range of different things, geopolitical, social, and so on, and combining together and serving them through an infrastructure, APIs and so on, so that people can actually start to query and interact with this virtual planet infrastructure or virtual planet capability. So it's, again, it's looking at the data services and how they're spread. We have, thankfully, so these slides were written yesterday, so I didn't know what I was walking into, but thankfully we have talked a lot today about the people side of it, not just about the computing, defining the capability and the mission clarity. And I'll go into the last piece, actually, more than anything else. Mission clarity. What actually is the purpose of Eve? What do you want to achieve? And until you have broadly at least 90% of the people in the room agreeing on what the actual mission is, it's not going to get very far, because you all have to pitch it to the politicians to fund it. And that means you've all got to be saying roughly the same thing. And so mission clarity, what is it going to do? Is it going to be focused on adapting? Is it going to be focused on migrating? Is it going to be focused on understanding? Is it trying to do all of those? Is it trying to do some of them now and some of them later? What actually is the mission clarity is a really important part, and that's one of the things that's held up some other initiatives in the past. The other thing I'm going to say is decide on a personality of the character of Eve, if you like. Are you going for good enough as soon as possible? This is an urgent problem. Climate change is an urgent problem. So do we want to go for the approach of what can we get stood up within 2 years? And we'll just do that. Whatever it is, 2 years of deadline, we're going to be up and running and live. Pace overrules everything. Or are you going to actually aim for what you want, what we need to achieve the grand visions of the program, aim high and take the time to get there right, which is what other large international collaboration projects have done over time, is taken the time to aim high. How soon? Based on experience with other things like this, like the square kilometre array and so on, I have a healthy degree of skepticism or caution, or call it what you will, that this thing will be up and running in any small amount of time. And by small amount of time, it depends on your ambition, of course, but as I said, SKA 20 years from at least that I've been involved in it, and you could argue it's not really in full production mode yet. So bearing in mind that the time frame could be long, bearing in mind all that we've heard about how supercomputing really justifies a huge return on investment and the impact of the climate community, I would argue that we need to be aiming much, much higher than you are already. Apart from anything else, politicians like getting involved in $100 billion initiatives, not $10 million initiatives. The bigger the better for politicians, particularly if it has an impact to go show that. So 30 megawatts is, I would argue, is way too low a target. If you were going to stand this up next year, 30 megawatts is too low a target. Given the amount of time it's going to get you to aim over the ground, 30 megawatts is a small part of what you need to be aiming for. And likewise, exascale computing will be maybe not ordinary, but at least ordinary enough for this kind of thing. So you may be aiming beyond that, I think. So I'm going to close with 3 suggestions. Build a capability, not just a machine. In other words, it's very easy to get distracted by building a facility and designing a supercomputer or designing multiple supercomputers. But focus on how you're going to enable the science of that, and on the use of that science, and how you're going to deliver the science out to the community, and build all of that into the capability. The machine is the engine, is an important part of that, but don't focus so much on that and say, well, we'll let the rest follow later. That's the wrong way around to achieve the best value. Do it the other way around. Design the capability, then figure out what machine you need to enable it. Apart from anything else, if you've got the capability described well enough and you're asking for the money for the machine to make that happen, that will be an easier sell to the funding agencies and to the political, and indeed to the public, than starting the other way around, which is, can we have a big machine, please? Reimagine what you think is possible. Don't start with, this is what we think is about achievable in the current time frame. Start by thinking, what really, if we just change some of those rules, we step bigger, what could be possible across computing, across people, across politics, across collaboration, especially if you're going to go for the aim high and get it right method. If you're going for the, we just need to get whatever we can done by the end of next year, then maybe you moderate that approach a little bit. And then the other thing I'll say is prioritize your people. More, as I said, the computing is a solvable problem. It's a very doable problem. Other people are doing stuff at this scale anyways, or have plans to do so. Prioritize the people. Then the paper was talking about 300 people per center. There's a slide this morning that talked about 250 people and so on. Where are they coming from? Out of universities, maybe. How are you going to hang on to them? Once the cloud providers' hiring headcount start opening up again in anger, how are you going to hang on to them? So there's a pipeline. It's not just where's the first batch, it's where's the pipeline. It's recognizing you have a pipeline of coming through. How are you going to process the pipeline? How are the skills going to change of those people based on what they need to know now, what they need to know in 5 years' time, what they need to know in 20 years' time over the life of this thing? Those skills will evolve, both in terms of the skills that are needed, but also the evolving skills of the people coming in at the floor. And then, of course, there's the global context you're operating in. You can't have people who come and work in a center anymore as an expectation. People don't really want that anymore. People want to be able to work located wherever they want. You can't ignore the politics either. And then one final point. Unless I'm mistaken, there's no lawyers in this room. And you want to model after ITER, CERN, ECMWF, SKA. Those are all international treaties. They're not science collaboration projects. They're international treaties. You don't get very far without a bunch of lawyers